In this mini lecture of the Soil Slopes and Streams series, we'll continue our discussion of mass movements. A prior video discussed rock fall, and we'll now go to the fast and wet side of the spectrum to talk about flows. Debris and mud flows are fast and wet mass movements. As you likely guess from their names, the difference in these categories is in the geologic materials that turbulently flow with water. Debris flows contain a variety of grain sizes, including very coarse debris like you see here, while mud flows are primarily mud and clay. Here we're looking at a debris flow in Las Lomas Canyon of California after a 2016 fire. You can see it develops rapidly, bouncing and carrying large boulders and debris. Because this debris flow is fluidized sediment, it can carry larger and heavier boulders than it could if it was simply water flowing down the channel. Debris flows are typically sourced from coarse soils on steep slopes, as you see here, and travel through channels as the one you saw in the video, and that you can imagine downslope of this person. When debris flows leave their confined channel at the base, they can be quite deadly, especially if that debris flow enters a river. In 2017, thousands of wildfires devastated California in an especially dry year. Following the fires, a storm dropped about 4 inches in just 2 days, much as a rapid torrent that destabilized slopes and debris in steep canyons. 23 were killed in this Montecito debris flow just outside Santa Barbara, and estimates from boulder marks and mud on trees indicate that the flows were 15 feet high. That this event happened in a wealthy neighborhood underscores how little is typically known or communicated about hazards in communities. And a feeling of safety regarding processes occurs for things that rarely occur twice in one place and typically not within several generations. There's an idea that because we haven't seen it before with our own eyes, it won't happen. But geomorphic change doesn't occur on the same time scales as humans look for, and sometimes it's punctuated by events such as this. It's a theme that will repeat in this series when we discuss hazards like landslides and floods. The combination of fire and rainfall is a 1-2 punch commonly linked to mud and debris flows. Rapid erosion and the loss of vegetation following fires leave steep slopes vulnerable to debris flows. Vegetation and especially tree roots help to stabilize slopes against rapid erosion, and they help water to infiltrate into the ground surface rather than running off the slope. The removal of vegetation and/or the burning of roots can mean that mud and debris are mobilized during a post-fire storm. Pause this lecture and visit the USGS site here to see how scientists link fire and flows and provide maps of risk to communities. Search the past years to find a fire in your state and view the risk map. For example, here's a map of debris flow risk in case a large storm followed a 2020 fire in the Bridger Mountains. Here, the risk map doesn't account for whether or not debris flow enters a channel, and it also can't predict whether or not the debris flow actually will occur. Lahars are a special kind of flow that generate off the slopes of a volcano. This mud flow in Lahar originated during the eruption of Mount St. Helens and covered a state highway. The eruption caused glaciers, ice, and snow in the mountains to mobilize sediment, fine volcanic ash, and debris, and it flowed over 100 kilometers or 60 miles downstream and downhill. These lahars were generated during the 1980 eruption that forever changed the shape of the mountain. Because of the interaction of this eruption with glacial ice and cold waters, the temperature of the mudflows, even tens of kilometers downstream, remained as high as 90 degrees. This is a pretty amazing map of Mount Rainier, just a 2-hour drive from Tacoma, Washington, south of Seattle. Red and yellow colors show the extent of past lahars that had traveled down slopes and rivers from the volcano. In fact, parts of the city are built atop these volcanic flows, indicating they might still be at risk during a future eruption. There's actually a lahar warning system for this area because of the high risk. Another type of flow is an earth flow. These are typically much slower than debris or mud flows, primarily because the flow is less fluidized or saturated and involves less water. This means they generally don't flow as long a distance, and they can often be identified by their characteristic rumpled topography. In the map and picture, we see 8 earth flows right at the northern entrance of Yellowstone National Park and close to the Wyoming-Montana border. Over 4 million visitors visit Yellowstone each year, and most unknowingly drive directly over these earth flows, including one which is actively moving and pushing the road. The final category of mass movements we'll talk about is landslides, which have a variable involvement with water and are generally thought of to be quite fast. Though sometimes used as a catch-all for all mass movements, landslides are often scientifically used as a term for a specific type, one which has a clear detachment plane on which the material slides. In this image, you can see the Mud Creek landslide in Big Sur, California. The slide detaches along a single failure plane and covers a road with 65 feet of earth extending out to the ocean. Some landslides detach and slide across a rotated surface, such as this one, the Oso landslide in Washington. You can see 3 things that are indicative of a rotational slide, such as the clear headscarp, blocks that are detached and rotated, and a rumpled toe. The Oso slide is also an example of how different mass movements can have complex morphologies that don't fit into perfect categories. When we look at the base of the slide, we see that it entered the river and fluidized. This meant it was able to travel farther than if the material hadn't become saturated, and it's one of the reasons the slide became so deadly, killing 22 people who were living or driving along the river. As was mentioned before, landscapes give clues to the legacy of processes, and this is true in the Oso landslide, where prior work had identified ancient slides in the topography, such as headscarps. You can see one of these headscarps curving in the background behind the modern Oso slide. Landslides and other mass movements can be triggered by a number of different events. We learned about the link between firestorms and debris flows, but earthquakes can also act to destabilize the ground. In 1959, a 7.3 magnitude earthquake shook Yellowstone National Park on a slope overlooking the Madison River. A large chunk of rock broke free of the mountain and plunged into the Madison River and across the valley. The slide buried 22 campers at its base, and an additional 6 were drowned in the waves as the disturbed river was displaced and splashed and crashed several kilometers upstream. The mountain was essentially cut away, and we can see the edge of the head cut here. The slide dammed the Madison River, creating what is known as Earthquake Lake today. The risk of the landslide dam breaking posed an even bigger potential disaster. So the Army Corps of Engineers cut a spillway, preventing the further rise of the lake. This picture is from a plane just after the slide and before the spillway was cut. One curious thing about the slide was how far it went up the other side of the valley. A unique occurrence that happens in large bedrock landslides is that if the mass of Earth falls rapidly enough and as a sufficiently large block, it can create a cushion of air that projects it further than it would otherwise, much like how an air hockey puck flies across the table. As with many natural disasters, the impacts are not felt equally by all. Disasters such as landslides have the greatest impact on developing countries and communities in poverty. Socioeconomic vulnerability is important when considering a person or region or nation's ability to prepare, mitigate, or respond.